We're very pleased to have Clare Burrage, who is an expert in modified gravity or alternative theories of gravity, and she's going to tell us how they can be tested. Okay, thank you.
Oh, thanks very much for having me. It's fun giving seminars around the world at the moment, even if we're stuck inside, largely still in the UK. So yeah, I'm going to talk, as the title says, about dark energy models, and particularly ones that we can test with tabletop experiments. So I'm going to sort of hopefully convince you over the next 50 minutes that actually doing experiments in the lab can tell us something about what's going on the larger scales in the universe. So roughly the structure of the talk is going to be that I give you a little bit of an introduction to dark energy. I understand this seminar series is largely focusing on dark energy, so hopefully won't spend too much time on that, but just to give you the context for what we're going to be talking about. And then I'm going to talk about why that motivates us to think about fifth forces in the universe. And then this concept of screening will come in, which some of you may have heard about, but I'll introduce and explain what's going on there. Then I'll talk a little bit in general about how we search for those types of theories, and then in particular in the last part of the talk come on to talking about a particular type of experiment called atom interferometry, and I'll tell you about how that works and why it's such a good type of experiment to look for theories of dark energy. Okay. But the main principle behind this talk is actually is a very old idea, right? Something that goes all the way back at least to Galileo, which is that the question of whether large and small objects fall at the same rate. Okay, so we all know, or the story goes, apparently this is apocryphal, but we can go with the story that Galileo dropped objects off the Leaning Tower of Pisa to determine if everything fell at the same rate, or if larger objects fell faster than smaller ones. But what we're actually going to talk about in this talk is the question of whether dark energy allows smaller objects to fall faster than larger ones. Okay, so slightly counterintuitive in the first place. But you might also at this point say, well, what is the point of listening to the rest of this talk? Surely we know at this point that we've tested the equivalence principle extremely well, and we know that in fact large and small objects do fall at the same rate under gravity. So I'm going to try and convince you that actually there are certain circumstances under which we don't know that to be true. We've certainly tested the equivalence principle for very many types of objects and very many circumstances. But there are situations that still haven't been explored yet, where the effects of a dark energy theory could be hiding and could kind of naturally be hiding. It's not super fine-tuned, and why they predict this kind of effect. Okay, so that's the picture you should have in mind of where we're going with this talk. Okay, but the motivation for thinking about this in the first place is really coming from dark energy, from understanding why the universe is behaving in the way that it is, and how we reconcile our observations with our theories. Because we know that within the standard models of physics and cosmology, it's perfectly possible to have a cosmological constant type term in the Einstein equations, and that cosmological constant term would drive an accelerated expansion of the universe. So that's not necessarily a problem. The problem comes when we try and ask what is our expectation for the size of that cosmological constant term, and our expectation from considerations in quantum field theory and what we know about the physics of the standard model is that would scale like the 4th power of the largest energy scale in our theory. Okay. So, you know, maybe if you're super optimistic, you would put that at the Planck scale. If you're really conservative, you might say, well, maybe we currently understand physics up to about the Higgs mass, something like that. But it's a high scale in particle physics terms. Unfortunately, the observed energy scale that corresponds to our the accelerated expansion of our universe is a low energy scale. It's about 10 to the minus 3 electronvolts. So many orders of magnitude smaller than kind of any natural scale we would expect for the cosmological constant problem. And then we get additional contributions to this cosmological constant from phase transitions in the early universe, which also induce large changes in vacuum energy. And so we have, again, at sort of particle physics-like scales. And so we have to explain why that's not showing up in the physics we observe, why the universe is accelerating at such a low rate. Now, I don't have a solution to the cosmological constant problem. I want to make it very clear that this problem still stands at the end of this talk, and as far as I know, there's no kind of broadly accepted solution to this problem. But there are two types of ways in which people approach solving this problem. Basically thinking about, you could sort of put them into two categories. One where you're thinking about modifying the left-hand side of Einstein's equations, so you're changing the theory of gravity, and one where you're thinking about modifying the right-hand side of those equations, so you're modifying the matter in your universe. Now, to some extent, you can map those two things into each other, so these are not sort of discrete categories, but there's certainly two types of approaches solving the cosmological constant problem. And when you think about doing that, so let's think about putting new types of matter into our universe. Now, the common thing that people do here is that they introduce a quintessence field or some sort of dark energy scalar field. And these are very commonly scalar fields, not universally, but introducing a scalar field is something that we like to do as cosmologists. When we have a cosmological problem to try and solve. And typically these scalar fields will be light, they'll be rolling in some sort of potential, and their dynamics help explain why the cosmological constant is not large in the late universe. The alternative approach, as I said, is that we modify the theory of gravity, and we say, despite the fact that GR is so well tested on Earth and in the solar system, maybe it's too much of a stretch to extrapolate that out to trust it without any modification to the theory on the very largest scales in the universe. And again, not universally, but a common consequence of modifying your theory of gravity is to introduce extra degrees of freedom. And again, a sort of common consequence of introducing those degrees of freedom is that you get extra scalar fields in your theory. Okay. So the philosophy that I'm going to take for the rest of this talk is that attempts to try and solve the cosmological constant problem commonly introduce light scalar fields. Okay. So whilst we're still not sure what the solution to the fundamental cosmological constant problem is, let's ask what is possible for these light scalar fields if we can either detect them or rule them out completely, or rule out certain types of behavior for these scalar fields. Then we learn something about what the solution to the cosmological constant problem should look like. So we're taking the sort of top-down approach, or sorry, a top-down approach would tell us that there's likely light scalar fields kicking around in our universe. But this talk takes the bottom-up approach of saying, well, what are those scalar fields allowed to do? If we constrain those behavior, that will tell us something about what the kind of what the fundamental theory must look like. Okay, I hope that's clear. That's where we're going with this talk. So adding extra scalar fields into your theory has been done for a very long time. As we said, they're one of the simplest modifications of a theory that you can do. So they've been extremely well studied. In the context of theories of modified gravity, some of the earlier work on this was done by Jordan and Dickey, Browns and Dickey, and that is the idea that you just add a single scalar field into your action for your theory, and it multiplies the Einstein-Hilbert term. So it's acting, if you like a dynamical Planck mass for your theory. Okay, so to set up the language, we're going to see a few times in this talk. This is our matter action, SM here. And these psi terms are some fermion fields which are moving on geodesics of the metric that's appearing inside the square brackets there. So we can think about the theory in this way, that matter is moving on geodesics of a gravity theory which has this extra dynamical scalar field in it. But actually you can recast that theory completely equivalently as a theory that has a standard Einstein-Hilbert term, so a fixed Planck mass now, a dynamical scalar field, but now matter is moving on geodesics of a different metric, so of a metric that also contains the scalar field as well. And this sort of single scalar field rescaling of the metric or of the Einstein-Hilbert term is the formulation of the Branson-Dickey theory, but actually that's very easy to generalize. And in the general picture that we're going to think about in the rest of this talk, you can think about matter as moving on geodesics that are rescaled by some general function of the scalar field. And that's the picture that I'm going to use in this talk. So we're going to be thinking about our extra scalar field, even if it's coming from a modification of gravity. We're going to think about it as interacting, as having most of its interactions with matter. So our matter fields are moving on a geodesic which depends on our extra scalar field. So that's where our fifth force is going to come from. That they're not just moving on geodesics of the background space-time metric, but of they're affected by the behavior of the scalar field as well. So what I've argued for you so far, or what I've tried to argue, is that thinking about dark energy and the accelerated expansion of the universe motivates us to think about light scalar fields in our universe. And if those scalar fields are present, a typical formulation of that theory would have them coupling to matter. So the argument from cosmology is that it's very likely that we would have these scalar fields around in our universe, and that they would be interacting with matter fields. Now at this point we run into a problem, because if you have new light scalar degrees of freedom and they're interacting with matter, then you would expect them to mediate a fifth force. And we've been looking for fifth forces for a long time. We've been looking for them on Earth and in solar system dynamics, and we haven't found them. And in fact, they're on certain scales, at least, they're excluded to an extremely high degree of precision. Now, excuse me. If you think about that that fifth force in the sort of simplest possible form for what that fifth force might look like, or in this case the potential associated with that fifth force, come up with something that looks like a very simple modification to the Newtonian potential between two objects. So we've got two objects of masses m1 and m2. They're separated by some distance r, so you have the standard 1 over r potential here. We're allowing for them to couple to matter with some strength that isn't the gravitational strength, so that's parameterized by this parameter alpha here. And if the scalar field that's mediating this interaction has a mass, then there can be some exponential suppression once you go beyond once the masses are separated by more than the Compton wavelength of the field. So constraints on this type of fifth force are extremely good. In these two plots, the yellow regions are excluded, and the left-hand plot is over the exclusions that have been done on short distance scales in the lab, and the right-hand plot on large distance scales within the solar system. And for this particular form of a fifth force, the most constraining results are from lunar laser ranging experiments. So if your fifth force is relevant on the scales of the Earth-Moon separation, then our parameter alpha has to be less than something like 10 to the minus 10. Okay, so that's starting to look like quite an extreme fine-tuning to satisfy these kinds of bounds. So At this point, we're sort of starting to see a tension between what our theories of cosmology want, which is at least a light scalar field, and that interacts with matter, and what our experiments are telling us, which is that we see no evidence of this scalar field so far. But the point that I want to stress here is that this picture that I'm showing you now is really only the very simplest form of the way that this light scalar field can behave. And actually, as soon as we allow things to be slightly more complicated, and in particular, once we allow for nonlinear interactions of our scalar field, so we allow it to interact with itself or in a slightly more complicated way with matter, then we get a much broader phenomenology, much richer and more interesting phenomenology, and suddenly our fifth forces are going to be allowed again. So going beyond the linear theory, which we were talking about on the last slide, is not such a strange thing to do, in fact, because the kind of physics that we're thinking about here, either we're thinking about it as a modification of gravity, which we know is a nonlinear theory, at least GR, or we're thinking about it as some sort of maybe a new fundamental scalar field in the matter sector. But in which case, the one scalar field that we do know about, the Higgs field, also has a nonlinear potential and non-trivial self interactions. So this is not, it's not a fully robust argument here, but it's just to say that there's no reason that there's no reason to forbid these nonlinear self interactions, and in fact, it's important that we do think about them and what they can do for our theory. And what they do is give us something that we call screening mechanisms. So, sorry. Apparently my voice doesn't work very well first thing in the morning. So the idea of screening mechanisms is to use the fact that the theory is nonlinear to try and hide the effects of our fifth force from experiments that would otherwise have detected it. So these very constraining experiments that we've been talking about. And the way that happens through the nonlinearities is that because once your theory is nonlinear, fluctuations depend on the background. So now the fluctuations that are mediating our fifth force depend on the environment that you're in. And thinking about that, you can find that you can make your theory have a weak coupling in certain environments. So in your experiment, suddenly your light scalar field doesn't couple to matter anymore. You can change the kinetic coefficients to make it difficult for your scalar to propagate and difficult for it to transmit the fifth force. Or you can make it, you can allow the field to change its mass depending on the environment. And that, again, makes it difficult for the scalar field to propagate. It makes it difficult to transmit the fifth forces over large distances. I think I'm going to skip this and move on to telling you. So specifically in this talk, we're going to focus on those theories where the scalar field changes its mass. Okay, those are the ones that I'm going to focus on. They're the ones that are the class of theories out of the three that I just told you about that are the most constrained by the types of experiment that we're going to go on to talk about, the atom interferometry experiments. And they also sort of illustrate quite a lot of the behavior, the screening behavior that we're interested in. So these are chameleon theories, and the name chameleon comes from the fact that they change their behavior to camouflage themselves depending on the environment. But more generally, at the level of the action, we can think about them as being a scalar field that has a canonical kinetic term, a nonlinear potential, and a direct coupling to matter. Now, already at this point in the action that I'm showing you here, I've made some very simplifying assumptions about what my matter fields are doing. In fact, I've assumed that we're just coupling to non-relativistic matter that we can describe as a perfect fluid. This rho here is the energy density of our matter fields. But this comes from the same form of the coupling to matter that we were looking at earlier. And I've made two choices here for the two unknown functions in our action, one for the scalar potential and one for the choice of the way in which our field couples to matter. Now, the fact that the coupling to matter is linear in phi is kind of a characteristic of these theories. The form of the potential is not so important. There are a number of other choices we could have made here, as long as we're not just picking m squared phi squared or some other, excuse me, or a linear potential in phi. As long as there are non-trivial self-interactions with the field, then we should get the same behavior that I'm about to show you. This particular choice of an inverse power law is motivated by theories of quintessence, so trying to maybe see if the dynamics of the scalar can also explain the cosmological history. But we could equally well have chosen lambda phi to the 4 or something similar here. But our theory is going to be characterized by these two energy scales, the capital lambda here controlling the self-interactions of the scalar field, and the capital M, which is controlling the way in which the scalar field interacts with that. And the capital lambda is going to be it's going to turn out to be quite a low energy scale, around the cosmological constant scale, and the capital M is going to be a high energy scale, so above a TeV scale, maybe all the way up to the Planck scale. And putting these, so looking at this theory, we can ask how our scalar field behaves. And the dynamics of the scalar fields are governed by this kind of effective potential here. So the bare potential that we put in, the inverse power law, and the coupling to matter gives us an additional piece here. And the two pieces together sum to give us an effective potential which has a minimum. Good, our field is stabilized. But the position of that minimum and the mass of fluctuations around that minimum are going to depend on the density of the environment. So you can see on the left-hand side here, in a low-density environment, minimum is very shallow, so the field is quite light. And in a high-density environment, the minimum is is quite steep, and the fluctuations of the field around that minimum are quite significant. So the field is very massive. Okay, so this is how we get to a theory where the field has a mass that depends on the density of its environment. So now we can sort of start to see that in higher density environments, it might be harder to excite fluctuations of our scalar field and higher to transmit our fifth force. This slide shows you in a little bit more detail how that really makes our field hide from the kinds of experiments that we've been talking about, which look for these extra scalar fifth forces. So what's going on here on the right hand side, we have another version of the potential we were looking at on the previous slide. So this is the effective potential as a function of the scalar field. The solid black line is our 1 over phi, our inverse power law, and the two dashed lines here are the contributions from the coupling to matter. One out in the background, some background density, and one the density inside a compact object. So our compact object is sat here on the left-hand side, and we're assuming that it's got some constant density inside. Now, what would normally happen if this was if this was the linearized theory, the kind of simple theory that we were talking about earlier in the talk, is that far away from the object, the field would sit in the minimum of its effective potential out here, so where the red dot is. And then as you come closer and closer towards the surface of the object, at some point as you travel across the surface, the density changes, and the field suddenly is moving in a different potential. It gets lifted up. It's now sitting higher up on the dashed black line, and it wants to roll down towards smaller and smaller field values. Now, without the nonlinearities that are coming from the solid black line, that field would just continue to roll down towards the origin, towards smaller and smaller phi values. And if that is the theory that you're interested in, you get something that looks very like the Newtonian potential around the object. And what that means is that the more mass you put in your object and the larger you make it, the deeper the potential that you're building up. So the potential, the amount of fifth potential, if you like, around this object is determined by how far a scalar field rolls between its value at infinity and the value that it takes at the center of the object. But if we turn on our nonlinear self-interactions, if we turn on the solid black line, then we see that there's a point past which our field can't evolve any further. It gets stuck in this minimum and can't roll to smaller and smaller field values. And that's putting a limit on how deep the potential can be around this object. And you could put more mass into your theory, into your source objects. You could make it denser and denser, and you still wouldn't build up any additional potential. Your field would remain trapped at this point inside the object. So you're limited into how deep your potential wells can be, and that's essentially the source of why we wouldn't have seen this type of theory in the solar system or in the experiments so far. So this slide is just saying that the same thing again in math, basically, that if you have sufficiently large objects, when large is determined in this inequality here by a combination, which is basically the compactness of the object, it's a combination of its density and size, radial extent, compared to the parameters of the theory, so the strength of the coupling to matter, which is our capital M, and phi background, so the background value of the theory. And if our object is sufficiently large, then what we were just talking about on the previous slide will happen, and the potential due to our additional scalar fields will be suppressed by a small factor here, lambda, which we can call a screening factor. If the object that we're interested in is sufficiently small or sufficiently diffuse, then actually the field never reaches the point, never reaches the minimum of its effective potential inside. And then we can't tell the difference between these two types of, we don't see any of the non-linearities of the theory, so everything behaves as in the simple linear theory that we were talking about earlier, and this suppression factor is no longer a suppression factor, it's just one. So in an ideal world then, you would say, okay, the reason that we haven't seen this theory so far is because all of the experiments I've done so far have been ones in which the test masses that I've used are so large or so dense that the effects of my scalar fields have been suppressed. They've been screened by the nonlinearities of the theory, and that's why I haven't seen it. But maybe if I can think about doing an experiment which uses unscreened test masses, and there are things that would be unscreened, so things like atomic nuclei, if you can do experiments on neutrons, or in the lab on microspheres, so micron scale objects, then you could think about doing experiments on unscreened masses. And this is what I'm going to talk about for the rest of the talk. But just actually before, so this is now, sorry, I'm going to pause. I'm going to carry on with that thought in just a second. But this is just to come back to the picture that we started with to make it clear what's going on. So now the reason that our light objects are falling faster than the large ones are because they feel the full effects of the fifth force, or if you like, the fifth force is pulling on all of their mass. Whereas for the larger objects, the fifth force is screened, it feels much, much less of the fifth force, or equivalently, the fifth force is only pulling on a tiny fraction of the mass of that object near the surface. And so it feels much weaker, it feels gravity, but only a very, very weak fifth force, whereas our smaller object feels gravity plus the full effect of the fifth force, and that's why it falls faster. Okay. That's the kind of emergent violation of the equivalence principle that you might want to think about. And we're going to think about that in the context of the lab. But before we do that, I just want to show you some results from a couple of years ago now, that have potentially seen some hints of this behavior on astrophysical scales. So this is work that's been led by Harry Desmond at Oxford, and they've been looking for exactly this effect, but not in the lab, instead in galaxies. And asking the question, if these theories are really kind of present in the universe, then perhaps different components of a galaxy will fall differently in the local gravitational field. So in particular, you could imagine stars being very large and quite dense objects. They would be screened from the fifth force, so they wouldn't feel the effects of the fifth force. But the gas and potentially the dark matter, depending on its nature, would not be. So the gas may be individual atoms or small molecules, or just dust but they're much smaller particles, and they wouldn't necessarily be screened by from the fifth force, and so they would feel its full effects. And so if they're both components of the galaxy are falling in a potential well, then the gas and the dark matter might fall faster than the stars, and the stars would lag behind. And so you can look for that offset, and you can also look for the resulting warping of the stellar disk lagging behind the center of mass of the galaxy. So those two tests were proposed back in 2009 and 2011, but the recent work has actually looked for this effect in large galaxy surveys. So they've used the Alfalfa survey and the NASA Sloan Atlas to look for these two effects. And surprisingly, I think to everybody, both searches come back as being consistent with the presence of a screened fifth force. It has quite a weak coupling to matter, so the strength of its interaction with matter is about 10 times the Planck scale, and it has a background constant wavelength of about 1.8 megaparsecs. The quoted significance of this detection in the papers is very high, but the authors do and would acknowledge that there are some really challenging systematics in understanding kind of whether galaxies would naturally show this behavior or not, or what kind of galactic dynamics might mimic this kind of behavior. So at the moment, I think it's still fair, despite this huge significance, to call this a hint rather than a real detection of a screened fifth force. But nevertheless, it's quite exciting that some interesting new astrophysics has been detected, which still needs to be explained. Okay, but we are going to come back to Earth now for the rest of the talk, and we're going to talk about atom interferometry experiments. And the reason why we're going to talk about atom interferometry experiments is because they're some of the best experiments that we do on Earth to look for this kind of behavior. So why atom interferometry in particular? Well, the first reason is that atoms are an extremely good test particle to look for these kind of screened fifth forces. So the plot that I'm showing you here is a plot of the parameter space of our chameleon theories. So if you remember, we said that there were two scales in the theory. One of them was capital M, which was the strength of the coupling to matter. That's on the horizontal axis. And one of them was a capital lambda, which was the scale in our scalar potential, the scale that controls the self-interactions of the scalar fields, and that's on the vertical axis here. And at the point where we started thinking about these terrestrial experiments, almost all of the parameter space that I'm showing you here was allowed. So that's 14 orders of magnitude on the horizontal axis, where the coupling to matter is the Planck scale on the right-hand side of the plot, and is 10 TeV, so particle physics scales on the left-hand side of the plot. And we've got 4 orders of magnitude on the vertical axis, centered around that capital lambda scale being the dark energy scale. Okay. So at this point, these theories were so good at hiding from experiments that their parameter space was essentially unconstrained, or at least enormous. And what we realized is, so what these dashed and dotted black lines are showing you, the ones in the center of the plot, are that everywhere above and to the right of those lines, different atomic nuclei, different atoms, will be unscreened. So they'll feel the full effects of the fifth force, okay, over a large chunk of our parameter space. So if we had a mechanism by which we could measure the forces on individual atoms, then we would have a really good way of probing a significant amount of the parameter space of these theories. And atom interferometry is perfect because that's exactly what it gives you. It gives you a way of measuring really, really precisely the forces on individual atoms. And now we can really imagine doing an experiment where we drop atoms, we measure the gravitational forces on those atoms, we see if that's consistent with GR or with Newtonian gravity, and if there is an additional contribution that would be due to the effects of our fifth force. So I'm just going to give you a really quick sort of theorist's view of how you measure forces on atoms in an atom interferometry experiment. So as the name suggests, an atom interferometry experiment uses atoms to do interferometry. And what we're using here is the wave-like nature of atoms. So this is really a truly quantum mechanical experiment. And we move the atoms around within our interferometer by poking them with a laser, essentially. And the way that we do that is illustrated in this picture here. So imagine, for simplicity, that we have a two-state atom, okay? Indicated by the big black circle, and we start with the atom in the lower state, so in the state 1, and we shine a photon on that atom with exactly the right energy to excite it from state 1 to state 2. Okay. Now, if our atom absorbs that photon, we still have to conserve momentum. So the incoming photon had some momentum, it gets absorbed by the atom. So after that has happened, our atom has to be moving with some velocity. Okay, so it's gone from being an atom at rest in state 1 to being an atom moving with some velocity in state 2. So that's how you can move the atoms around, by interacting with the laser beam. But the additional thing that we do with these experiments is to say, well, what if we didn't observe the atoms at this point? Can we set it up so our atom is now in a superposition of states, one of which it didn't observe it didn't absorb the photon and is still at rest, and the other where it did absorb the photon is now moving with some velocity. That's the principle that is underlying the interferometry experiment. So this is a sketch of the position of our particles, of our atoms, as a function of time. But it's not actually the position of the atoms, it's the position of the center of mass of the parts of the wave function, because now we are going to put our atom into a superposition of states, okay? But in all other respects, it behaves like a standard interferometer that we all know and love. So we have, if you think, we have a beam of atoms coming in from the left-hand side, we have a beam splitter here, that's the first interaction with the photons. There's a second interaction with the laser beam, which acts like the mirrors to bring the two paths back together, and a third interaction to recombine them. So it's really, the principles behind this are the same as those behind any other kind of interferometer, an optical interferometer that we know and love. The difference is here, for example, in this first interaction, our atoms were in the ground state. And then we're now putting them into a superposition of states, one of which gets kicked up and one of which doesn't by the interaction with the photon, by the interaction with the laser beam. And then when they're moving freely, we're assuming that there's some there's possibility of some acceleration in the x direction. So between the laser pulses, the atoms are freely falling. And as the atoms travel, or as the parts of the wave functions evolve along these two different paths and are recombined, you find that they pick up a difference in phase. So there's an accumulated phase along the two paths, and also a difference in phase from the different interactions with the laser beam at the two separate points here. And those combine to tell you that the probability that you see your atoms in an excited state at the output of the interferometer is a function of k, which is the wave number of the photons in the laser. So that's something you control with your experiment. Of the time t, which is the time between the pulses of your laser, and a, which is the acceleration that they've felt as they're freely falling between the pulses. So if you can measure the number of atoms in an excited state at the output of your interferometer, and if you know the time between the pulses and the wave number of the photons in your laser beam, then you have a direct measurement of the acceleration that they've experienced within your experiment. And it turns out that that we can make those measurements really, really precisely, and so we get very good measurements of the acceleration of our atoms. Okay. So to do this, to look for our chameleons, for our dark energy models, we do this within a vacuum chamber in the lab. We have to put a source mass inside the vacuum chamber. This is the black and blue circle here. So the picture here is of our scalar field, our scalar potential inside a vacuum chamber, which has walls at plus minus z. So the red curve here is what the field would look like if the vacuum chamber were empty. If we put a ball at position 1, then the scalar potential is the dashed blue line. So we get quite a sharp gradient in the center of the vacuum chamber. And that's where we hold our atoms and we see if we can detect them falling down the scalar gradient. We can then move the position of the ball of our source mass from position 1 to position 2 and see if any signal that we're seeing, that we're interpreting as an additional attraction towards the ball, changes sign as we change the position of the source mass. So we proposed this experiment back in 2015. In 2016 and 2017, it was actually performed first by a group at Berkeley who already had an existing optical cavity that could do these atom interferometry experiments. So their setup here has an aluminium sphere, and they hold cesium atoms above that sphere, and they look for any additional acceleration of the atoms between the atoms in the sphere. Now, because they were using an existing setup, the orientation really is the way that you see it on the slide. So you're looking for an additional acceleration between the atoms and the ball, or the aluminium sphere, on top of the fact that these atoms are already falling towards the Earth, which is at the bottom of the slide. So you are looking, they've done this experiment with a hugely, incredibly precise result. But there is a particular challenge here, that they're looking for a small signal on top of a large background, because these atoms are falling towards the Earth anyway. So this was, sorry, I'm just speeding up a little bit to make sure that I get to the results by the end of the talk. So this was the experiment that was done by Berkeley.
Can you go back to the plot and explain it? What's K plus and what's K minus?
Okay, sorry, I won't speed up then. I'm happy to tell you what's going on here. Right. Yeah. So what's here on the vertical axis is the acceleration that the atoms are experiencing, subtracting off the acceleration due to free fall of the surface of the Earth. So there's two sets of two possible choices you can make for what you're doing here. You can hold the atoms close to the sphere or further away. That's the difference between the red points and the blue points. Okay, so if there is a signal that we're seeing due to the attraction of the atoms to the sphere, you would expect to see an offset between the red points and the blue points, because the further away you are, the smaller that effect should be, right? And obviously by eye, you don't see any offset here. The other choice you can make is in your interferometer, whether you kick your atoms towards the sphere or away from the sphere. So that's the difference between K plus and K minus. So they're exploring different systematics there, but also slightly different regions of the scalar potential as well. And then K average is the average of the K plus and K minus.
So this looks like a null result, yeah?
Yes, so yeah, not to give away my punchline, but no, there has been no detection of this force in either of these experiments. Yeah. Okay, is that all right? Should I carry on?
Yeah, thank you.
Yeah. So this is yeah. We also have, I should say, the group of Ed Hines, to the Centre for Cold Matter at Imperial College in London, have also done a version of this experiment. And this is largely a photo just to prove to you that this experiment exists. What we have here is the vacuum chamber here, this large cylinder. Over here on the left-hand side is the oven from which our rubidium atoms are extracted and injected into the chamber. And then on the ports from the vacuum chamber, there are the kind of laser inputs. And then there's another optics table where the lasers are generated. And so we've done a version of this experiment as well. Largely well, there are a number of differences between what we've done and what the Berkeley group has done. One of which is that we've used rubidium instead of cesium atoms. But the key difference, I think, from a physics point of view, is that now we have the orientation of our experiment is that the atoms are held. We're measuring forces horizontally, if you like. So we have, in principle, a zero background experiment, that we're not sensitive to the acceleration free fall at this. Yeah. So we have a slightly less precise bound on the size of this anomalous acceleration, but nevertheless sort of reasonably comparable and with largely different systematics. And then I can show you what this looks like here in terms of the parameter space that we were talking about earlier. So if you remember, on the horizontal axis, this was the coupling to matter, normalized to the Planck scale. And on the vertical axis, the scale in the scalar potential, capital lambda, normalized to approximately the dark energy scale. Excuse me. So you can see again that this central region of the plot was previously allowed, and then the atom interferometry experiments that I've been telling you about, our work in the blue bounds, and the previous Berkeley experiment results in the sort of beige have excluded almost all of this central region. So the previously existing constraints that we're showing here, the green curve coming from torsion balance searches for fifth forces, and the orange bands coming from the fact that if our theory was sufficiently strongly coupled, you would actually perturb a hydrogen spectroscopy. You would see additional forces between electrons in the nuclei and hydrogen. So a huge amount of what was previously available parameter space has gone now from these experiments. There's still annoyingly a tiny window left here, this sort of triangle between our constraints, the torsion balance constraints, and the dark energy scale here towards the right hand side of the plot, which we would really like to cover. Arguably, this is where the most well motivated theories live. If you're thinking of this coming from a modification of gravity, then you would expect the coupling to matter to be around the Planck scale. And if you're thinking that this is connected to a solution to the dark energy, to the cosmological constant problem, then the other natural scale in your theory is the cosmological constant scale. So really, this is where you would expect your theories to live, arguably, and there's still some window there. So we would really like to, and we're trying to find funding to continue this experiment to exclude this last window of the parameter space, but at the moment, obviously, it's down. And then I think I've been talking for the best part of 50 minutes now, so I think actually that's the key point that I wanted to say. I can flag up that I'm happy to talk about other types of constraints on these theories, where they come from. slightly different choices for theories and what we might be doing in the future. But I'm going to skip to the summary and say that what I've tried to convince you of in this talk is that explanations for dark energy typically introduce new scalar fields that would couple to matter, but the corresponding long-range fist forces so far haven't been seen. But if we think about the full phenomenology of a scalar field theory, then we show that theory to be nonlinear. And once we do, there's the possibility for a screening mechanism which hides these fist forces from our experiments. Nevertheless, you can still do sort of targeted experiments that are really focused on the types of situation where your fist force is most easy to detect. And it turns out that atom interferometry is a particularly powerful technique. And what we're doing here, I think, is really nicely complementary to large-scale cosmological surveys. So we're adding, it's not either or. We're adding in new information to understanding dark energy from the lab, from small-scale terrestrial experiments, compared to what you can do with a longer-term, large-scale survey. Cool. Well, with that, I'll stop there, and thanks very much for listening to me.
Okay, I guess thank you very much, Claire. Any questions or comments? Anybody here? Stephen?
Hello, can you hear me?
Yep.
Yeah, so thanks for the talk. It was very interesting. So these experiments are located on the Earth, which is actually a very strong gravitational field compared to the cosmological scale. So I was a bit confused as to whether the whole system is screened or not. So yeah,
no, that's a very good question, and you're absolutely right. That is something that I skipped over, that I should have told you. So let me just go back to our sketch of our experiment. Yeah. So yeah, you're absolutely right that we're doing this experiment at the surface of the Earth, within the solar system, within the galaxy. So you might well expect to see, it's a very reasonable question to ask if our fist forces are screened within the solar system, and that's why we're not seeing any effects on the orbits of planets, wouldn't that also apply to anything that we can do on Earth? And the reason that's not the case is because we're doing this experiment within a vacuum chamber at the surface of the Earth. So suddenly inside our vacuum chamber, we have a very good underdensity, if you like, surrounded by the dense walls of the vacuum chamber. And the fact that the walls of our vacuum chamber are sufficiently dense and sufficiently thick, I mean, this is not, this is just an off-the-shelf vacuum chamber, it's not anything special, but the fact that they're present mean that the mass of our field is sufficiently, the field is sufficiently massive in the walls of the vacuum chamber that essentially acts as a boundary condition for the field there. So the field is fixed. Regardless of everything else that is going on, the field takes one particular value in the walls of the vacuum chamber, and that's the value that minimizes its effective potential there. And that essentially decouples what is going on inside the chamber from what is going on outside. And that's also why we don't have to worry about if the fist force is due to, cars driving past outside the vacuum chamber as well, is that the walls really shield, certainly as far as the fist force is concerned, shield the interior of the vacuum chamber from the exterior. And because the interior is, we have such a good vacuum, actually, things are able to become unscreened there.
Okay, thanks. So it depends on the boundary conditions which affect your wall.
Yeah.
Okay. So if you had a different boundary condition, you'd see something different. Well, I suppose because you don't see any signal, then
Yeah.
Yeah, you don't see.
But you could think about what you could do to sort of optimize things. Certainly, if we could make the vacuum chamber somewhat bigger with the same quality of vacuum and the same sort of screening due to the walls, the same boundary condition in the walls, then the gradients due to our fifth force could become bigger. So you could imagine playing around with those boundary conditions to try and optimize your experiment. Absolutely.
Okay, that's great. Thank you.
Benjamin?
Hi.
Hi, thanks for your talk. That was very interesting. Did I understand correctly that the constraints that you presented are essentially for Chameleon models only?
Yes, the ones I've shown you are for Chameleon models only. I think I have as a backup. So this is essentially the same plot on the left-hand side, but on the right-hand side, these are the equivalent constraints for Symmetron type models. So I don't know if you know those theories, but those are instead theories that screen by changing their coupling constant. Essentially, the coupling constant goes to 0 in dense environments, whereas the Chameleon works by changing the mass. It's a little bit harder to plot because that's a 3-dimensional parameter space. So these overlapping curves are trying to indicate the third dimension of this plot. We're still trying to come up with a nice way to visualize that. So they're not. So we do have constraints on other types of theories as well. It's not quite as powerful an experiment in terms of constraining those models as for the Chameleon, but it does constrain them as well.
Thank you. And so if we manage to constrain basically those mechanisms on, on a much broader range of scales, what's the prospect for, surviving for modified gravity in general? Like.
Oh, yeah, that's a good question. It's a tricky one, because it's absolutely true. So the third type of theory, which the third type of screening mechanism for modifications of gravity, which these types of experiments absolutely don't constrain, is theories that screen through a Weinstein type mechanism. So because they have a more complicated kinetic structure for the scalar fields. But those theories are now under pressure from the cosmological side, either because they predict wrong sign ISW type effects, or because they predict that gravitational waves travel at a different speed to that of light. So it really has become, I would say in the last kind of 5 or so years, that modified gravity is now suddenly actually quite difficult to, or certainly you don't have the huge amount of freedom that we previously did to modify gravity without worrying too much. You could say that that's a good thing, that potentially these constraints mean that we're homing in on a correct theory. It's just possible at the moment that we're homing in on the fact that GR is the correct theory. The caveat to all of that, I think, is that we really haven't tested these things on galactic scales as much. So we haven't tested modified gravity. We've tested it now very well, I would say, on Earth, in the solar system, and so in our local environment, and on cosmological scales. But there is a gap in our understanding about what could be happening on the scale of galaxies. And there it's tricky to have a big degeneracy or a potential degeneracy with what you think your theory of dark matter is, or what you think the dark matter distribution in the galaxy is. So that's kind of the natural explanation for why we haven't got good constraints on those scales. But nevertheless, I think that's probably what we should be thinking about in terms of prospects for modified gravity. If there is scope for large effects, I think galactic scales are where they're likely to be.
Okay.
Thank you.
All right.
Okay, Claire. So this was all for the baryonic sector, right?
Mm-hmm.
Yeah. So Yeah, actually, what's interesting about Harry Desmond's paper is that he's looking for a differential fifth force between the dark matter sector and the baryonic sector.
Mm-hmm.
And I think basically if he doesn't allow, so basically if there's no screening allowed, then basically the constraint on delta G effective is really, really tight.
Yes.
So it's kind of difficult to interpret the results of this paper, but essentially you're saying that basically with a screening mechanism that basically there seems to be some preference, there seems to be some evidence for at least modified gravity, right? Or a fifth force.
Yeah, I think that's right. I think if you interpret this result as new physics and as a fifth force, then it has to be some sort of screened fifth force, because you're seeing something that acts differently on the stars compared to how it's acting on the gas and the dark matter. So that actually probably also means that you have to make some assumptions about what the dark matter is as well, because if it's, I mean, for example, in an extreme example, if the dark matter were actually all made up of black holes, then you wouldn't expect those black holes to have any scalar charge at all. And so they wouldn't feel any of the fifth force.
Sorry, Claire, could you just have dark energy coupled to matter? Would this also not work? Like if your dark energy doesn't couple to, at least you don't see have a fifth force in the baryonic sector, but you'd have a fifth force in the, like there's no need for a screening mechanism, is there?
So I think it depends. So this is where we're getting into galactic physics that I'm less sure of, but you're seeing an offset also between the stars and the gas, and it depends whether the gas sufficiently well traces the dark matter even without an additional coupling.
Yeah.
So if I mean a coupling, if yeah, okay, I think you understand what I said, yeah.
Okay. And I think there's another question from Cassie.
Mm-hmm.
Yes, from Christoph. Yeah. To the same slide, actually. When they did, I haven't read the paper yet, but did they consider any RAM pressure stripping or any gas effects that essentially would give you the same effect? Like, yeah, there's stars and gas behave differently in infall because gas interacts with hot gas in the halo of a cluster or group or whatever. And did they disentangle those or?
So I should start by saying you should take my answer to this question with a pinch of salt, because you know, although I've read their paper and talked to them about it, I'm not an author of this paper, and I can tell you with a huge amount of confidence what they've done. They certainly don't model those effects on a galaxy by galaxy basis. They try to take them into account within the model that they're fitting in terms of allowing for statistical noise that would seem to be consistent with what we know. But I do think, you know, there is scope for an explanation along those lines, if you could explain why kind of galactic physics. So you need an effect which is correlated with the direction of the local gravitational potential, or potential gradient rather. And it's not immediately obvious to me or to them in the paper that the kinds of physics that you mentioned would have that correlation, but maybe a closer study would show that it does.
Okay, thank you.
Actually, Claire, I have one more comment, right? It's related to quintessence, right? So in quintessence, in the simplest model, well, for all potentials, you can essentially prove that H0 goes down relative to lambda. So basically, if you replace lambda CDM with any dark energy model that's based on quintessence, then you would expect H0 to be lower than it is in, say, Planck. If local determinations turn out to be high, then this would disfavor quintessence. I mean, is there any way of getting at these chameleon models in exactly the same way? W effective, I mean, what you expect is that if W effective is greater than -1, then H0 should go down. So this is a much simpler way of, I mean, at least we can expect that in the next few years, they will have a good determination of H0.
Yeah, it's possible. Yeah, no, you're right. It's possible that that might. So the one thing that again I just very briefly skimmed over, but let me just mention this a little bit more detail, is that there is, or even for these chameleon models, really another dimension to the parameter space which you should think about, which is really what is the form of the potential. Everything that I told you was choosing just a 1/5 potential. But you can think about allowing that to vary, and I guess actually what the kinds of measurements that you're suggesting actually potentially might tell you something about what the shape of the potential has to be, how much evolution you can have on cosmological scales, and that actually might be quite a good way of constraining this, the freedom in the choice of potential. That's quite interesting.
Thanks. So any more questions or comments? Nobody here? No. Okay. Well, thank you very much, Claire, for the very interesting talk. Okay, more or less it.
Thanks very much for having me.